For the next 2 weeks and beyond, we'll be spending a lot of time discussing and applying Newton's 3 laws of motion. The first 2 laws can be captured by this simple symbolic statement. The sum of the forces means that on any object we examine all the forces acting on it, and if we add them together as vectors, they will be equal to the mass of the object times its acceleration. So we can rearrange this in several useful ways. If we solve this for acceleration, we get this equation, and it tells us that the acceleration that any object has will be a result of the net force, the sum of forces. We also refer to it as the net force. The net force acting on an object divided by its mass. And the mass we consider to be its inertia. Those 2 words are synonymous, mass and inertia. And we can think of inertia as the resistance to change in velocity. You remember, change in velocity is acceleration. So if an object is massive, it's hard to speed up, hard to slow down, and hard to change direction. I often use the image of an oil tanker. It's a lot of mass, very difficult to speed up, very difficult to slow down, and very difficult to turn or change direction. Another thing to notice about this statement that I've written, I'll rewrite it, it's so important, is that if the sum of the forces is 0, then the acceleration is 0. Or if we see an object whose acceleration is 0, then we know that the sum of forces must be 0. That's related to the usual statement of the first law, the familiar statement that an object at rest stays at rest, and an object at motion will stay in motion at a constant speed in a straight line. So an object moving at a constant speed in a straight line is subject to a net force of 0. Sometimes this is not immediately intuitive or obvious. You'll see when we do problems involving this kind of situation. The other important thing about this equation is that it's a vector equation. So when we use it in problem solving, we always write it this way first, this way. So this is the format that I will follow and you should follow whenever you're solving problems. Sum of the forces x equals max. In some cases it will be 0, in other cases it won't. And the sum of the forces in the y direction equals the mass times the acceleration in the y direction. We always begin our problem solving with this statement. The third law, so this, what I've been talking about is the first 2 laws. The third law is usually spoken of as the action-reaction. For every action there was an equal and opposite reaction. I don't think this statement is particularly informative. A clearer grasp of the third law is that all forces are interactions between two objects. So we've talked in class about how a car moves forward. A car moves forward because the car, when you step on the gas, the engine turns the axle turns the wheels push on the road, and the road, or the tires, let's say, the tires push road, and with an equal and opposite force, the road pushes the tires or the wheels and the car as a whole. Let's go to page 2 since we've run out of and let's look at several other examples. A bat hits a ball. The ball goes this way, and the bat doesn't go backwards, it just slows down, but it has an equal and opposite force that way. A swimmer pushes on the water, and the water pushes back on the swimmer. Fan cart. Fan pushes the air, air pushes the fan. So those are equal and opposite forces. Now, in each case, there are two objects. Two people in a canoe push on each other, and what happens? Both people move apart. Now, although the force has to be equal and opposite, the accelerations may not be equal and opposite. So if the person in one canoe is a big, heavy person, and the person in the other canoe is a wiry, thin person, the forces are still equal, but, right, that's the force of the big person on the small person, and it's equal and opposite to the force of the small person on the big person. It doesn't matter really who does the pushing, whether they both push or the small person pushes or the big person pushes, the force will in fact be equal and opposite. But the accelerations may not be, because the more massive person, the person with the bigger inertia, will have the smaller acceleration. So force on the big person equals the magnitude of the force on the little person, but since it is the mass of the big person plus the acceleration of the big person equals the mass of the little person times the acceleration of the little person. And if we divide these things so that we get the mass of the big person divided by the mass of the little person, that will be equal to the acceleration of the little person over the acceleration of the big person. See, they're inverse relationships. The bigger person has the smaller acceleration, and the smaller person, the less massive person, has the bigger acceleration.